Will this ball be? It's got a hat-trick. Second Indian to take.
Top-class players. Mohammad Yusuf and great nick as well. Look at this, a great delivery going through the gate.
Beautifully bowled there by Wasim, and he's got Darren Lehman with the Yorker.
Very difficult to negotiate these swinging Yorkers. Started well outside off stump. It was on his foot before that bat could.
Will this ball be?
These are two of the examples, good examples of swing ball in cricket. Have you ever thought why would the ball, while in motion and while it's coming towards the batsman, can change its direction while in the air? These are fascinating. This is a fascinating question which we would like to answer in this course. What we are going to see later on is that the thin layer of air in contact with the moving ball, on two sides of the ball, they undergo different transport processes. On one side we are going to have laminar flow, and on the other side we are going to have turbulent flow. This difference in flow pattern on two sides of the ball create a pressure gradient which would make the ball move while in air. So there are examples of moving objects changing its direction, moving objects experiencing force while it's in contact with a fluid. So this course will try to give you an idea of the different transport processes, the mass transfer process, the heat transfer process, and the example of what that you have seen just now, the momentum transport process. And we would also see that these seemingly different processes, mass, momentum and heat, fundamentally they are the same, because they are governed by the same type of equations which essentially connects the cause and the effect. So the cause of heat transfer is temperature gradient, the conductive heat transfer is temperature gradient, and the effect of that is flow of heat. And these proportionality rules, they have a constant associated with it, which we know as the thermal conductivity. Similar equations exist in momentum transfer as well as in mass transfer, giving rise to two other transport coefficients, namely the diffusion coefficient and the viscosity of the liquid. So this course would like to see explore the similarities between these processes, and at the same time you would see that technology demands that we understand all the newer processes which are coming up. So whenever you come across a process which you would like to model for eventual scale up to the industrial scale, you would find that understanding the physics of the problem is extremely important. So how you understand the physics and how you can express that physics in terms of mathematical equation, that essentially holds the key for any scale up process. And examples of new processes coming up are ubiquitous in nature. Wherever you see any new technology, especially involving material science, chemical science, nanotechnology and so on, and in newer fields such as microfluidics and others, there is definitely a demand to understand the process, to model the process, to derive or to obtain the design equation of such process. How do we do that? In this course we are going to give you a structured introduction of the fundamental forces in action in these transport processes and what that binds these processes together. So if I look at the way the different concepts are going to be involved in here, I'll quickly bring your attention to this, where this is as I said is a BTech level course. Also it's suitable for MTech as well as MSc, and we need only a undergraduate level course in fluid mechanics and heat transfer, and introduction to mass transfer is preferable, but it is not absolutely necessary. And I have also listed some of the textbooks that would be followed in this course. Therefore, the summary of the course can be to explore the link between momentum, heat and mass transfer, which are similar in nature due to the basic underlying similarities of the mathematics and the molecular mechanisms which describe such processes. So, therefore, if I look at take a quick look at the course plan, in the first few weeks we go through the fundamentals of momentum transfer. We would formulate the equation of motion, the Navier-Stokes equation, we would see its applications, and then we will move into boundary layers, the thin layer adjacent to a solid boundary where heat, momentum or mass transfer is taking place. So, we will go do a quick mathematical treatment of the concepts of boundary layers, the transport in boundary layer, how we can handle both laminar boundary layer and the more prevalent turbulent boundary layer, what is drag and how do we handle how do we express drags for different situations. Then we will do similar studies in heat transfer. So, the solution of heat transfer in laminar flow, then the more general approach of developing the energy equation, and we will also see the transient conduction, the different models which are available for explaining transient conduction, and finally, we will move into mass transfer in the development and use of species balance equation and the natural convection, the relevant examples from heat and mass transfer. At this point, we would start to see that these processes, three processes, heat, mass and momentum transfer, they have significant similarities in between them. So, how can we mathematically treat this similarity between heat, mass and momentum transfer, and we would see that some similarity parameters and analogies can be obtained out of these treatments, and this would enable us to model, formulate, model and solve coupled heat, mass and momentum transfer problems based principally on analogy. So, this course would therefore give you a complete idea about the transport processes, their interconnections, similarities, and it would also train you to model a process for which design equations are not available. But those processes are becoming so important that you need equations, relations, understanding for ultimate scale up to industrial level. So, that is what transport phenomena course is all about.